continue with his lectures.
Thank you. Okay, so Felix. So look at this. So I've changed the LaTeX package for MatCal. So then many letters have changed. Like the reconstruction will be different now, and the D gamma will be different. What is it? So now the reconstruction is a bit less nice. Yeah, the D is different, but I had noticed that the I was unfortunately different. Okay, so yes, a few small comments. So first, there is a technical detail which is somewhat unfortunate, but apparently it is impossible to get rid of this. So in fact, when you work with the green kernel, you have to split it into two parts, K and R. So R is smooth and K is with compact support, so it contains the singularity at the origin. Okay, so this is unfortunate, but I've come almost to accept it, and while you already truncate it, so you ask for an additional property that K integrates to 0 the constant function and a few monomials. So for us, actually, the first ones, and actually only in space. I forgot to write here from 1 to 3. So anyway, also time if you want. Okay, so we will see later where this plays a small role. Okay, so in particular, when I define my canonical model, yes, here you remember yesterday maybe I had the G convolution, so everywhere now I should have K convolution. Okay, it's a small change. Another comment is that in fact in Martin's paper there is okay this tree was missing in the list, and maybe you remember, actually we discussed it. I said no, actually it's not there, but it is there. So anyway, I've added here, it has homogeneity 1 minus 2 kappa, so almost 1, and then I computed somewhere it's pi. Where is it? Here. Okay, it's like the other ones, it does not change much. But okay, so you will see it appears at some point. Okay, then we defined this canonical model. I remind you, it is very important that I call it canonical because I have this multiplicativity with respect to the pointwise multiplication, which is the standard, the canonical multiplication of real valued functions. Okay, so again, this is intuitive, it's the natural choice, but this is exactly what we'll have to drop. Okay, not yet today, but tomorrow for sure. And yes, okay, so this is the first model you see in my lecture. So you have seen other models in Felix talks. So this we did yesterday, blah, blah, blah. Okay, this was the definition of D gamma. Yeah, this was this example I gave. Sorry, I'm just going quickly. Yeah, okay. I wanted to put at least once more, say, complete definition of a model. So you have a regularity structure. So one model is a pair of operators, say, so one which is pi x from t to distributions, which is linear for any fixed point x. So once again, x is the base point, while gamma xz is a linear operator. Okay, here, sorry, G is the structure group, but anyway, you just consider linear operators here from this. Okay, T is the linear span of my initial symbols, of my trees, okay? and then you have these properties, which are, say, nonlinear requirements again, and plus you have these analytical properties, which are very important, but I do not repeat them here. I want to repeat once more that the distribution pi x tau of, say, dot of y are generalized monomials in the variable y centered at x. The operators gamma x z are used to compare coefficients at x and z. It's like in manifolds, you have 2 points. In principle, they have nothing to do with each other, so you must specify a way to compare what happens at x with what happens at z. Okay, and now, until now, we have only seen one model, which is in particular multiplicative, but the theory is built in order to work without this assumption, and indeed it does not appear in the definition of pi x. While, okay, gamma is, yeah, by the way, yes, you can see that you can multiply gamma by gamma, and you get another gamma, at least if you choose correctly the base points. You can multiply pi by gamma, but you cannot multiply pi by pi. Okay, so this is the point. In general, you do not require. Okay, and yeah. Okay, we'll see. We'll come back to this later. Also, reconstruction. I want to put on one of my slides the more correct statement. For any model and gamma positive, there exists a unique linear map from these model distributions to distributions, such that, okay, this was the formula that Felix explained with this rescaled function, okay, and so more informally, it's easier to understand this. You have this, that for any fixed point x, the distribution is correctly described by this quantity, okay, with an error which is controlled by x minus y to the gamma. Okay, this is informal because when these are true distributions, you don't even have the right to compute them at y. So what you do have the right to do is to compute them on some test function. Okay, and then you want that you have this behavior. Okay. Okay, so this theorem is the main tool of the whole theory. So I have here a short discussion of this fact. So remember that U, this model distribution, so has this expression. So it's a sum of functions multiplied by symbols. Okay, so it's so the coefficients are proper functions of x. They are not distributions of x. Okay, so here there is no distribution actually. The distributions are only inside the pi x of tau. So even gamma contains only good functions. Okay? So when you compute pi x of u of x of dot, that's okay. So it's a distribution. Okay, because you are multiplying this distribution in dot times something which is a function of x, but you are decoupling the two variables, so there is no problem. In fact, what you would like to do is to compute this at x. Okay, so this you can do when the pi x of tau are all continuous functions. So this is really one of the results of the theory. So when all these objects are continuous functions, then the reconstruction is just given by this. Okay, in general, the existence of RU is much more difficult, and so this is the main result, okay, of the reconstruction theorem. So you have some object which replaces this evaluation at x. Okay. And yeah, I made the analogy between this formula and So maybe I go back 1 second, and yeah, this classical Taylor expansion. So you are Taylor expanding distributions, okay, on a fixed basis. But the point is that your model must be well defined, and this is, in principle, is not easy. You will see that, okay, in particular, all the algebraic and the analytical requirements are easy in the smooth case, but when you go to rough models, it's much more difficult. But at least you do this on objects that you know, that you control by hand. Okay, so yeah, you control them by hand because you see. So okay, this is the gamma. Where is the pi? Yeah, the pi is given, as you see, by explicit functions of your noise and of this truncated green kernel. Okay, I told you this is not going to converge, in fact, but some clever modification will indeed converge and still satisfy the properties. Okay, so this will converge as distributions, and here you do have products. For instance, this thing is, or maybe this thing is a square. Okay, so you are computing, in some sense, the square of this distribution. You see? So you can define some products of some distributions which are explicit, and then this will be your building blocks for the equations, for instance, for the solutions to the equation. Okay, but today I still want to define so do other computations. So this we discussed, okay, again, reconstruction is really the crucial result. Now I repeat also the integration theorem, in particular what I need. So let gamma positive. Now there exists a unique linear operator k from d gamma to d gamma plus 2. Now 2 is because we are in the green kernel setting, otherwise it can be more general, such that, so r k of u is equal to, so the other k, not mathcal k, convolution r of u, which means, so let's look at it the other way. So you reconstruct u. So you have a distribution. You take convolution with your kernel, okay, and then you ask yourself, what is the Taylor expansion of this? So I knew the Taylor expansion of Ru. It was u. So capital U. Okay. What is the Taylor expansion of Ru? Sorry, of k convolution Ru? Well, it's k of u. Okay, so this theorem is telling you how you can write the Taylor expansion of the convolution between your object small u and the green kernel g or k. Okay, and in fact, so this looks a bit maybe strange again, but the result is somewhat not so difficult to write down. So okay, in our 543 setting, gamma is 1 plus 3 small kappa. This is what, okay, we'll see below why this value is good enough. Okay, then notice, by the way, that I don't, okay, to one point I need the plus 2, but most of the time, for me, d gamma plus 2 is actually inside d gamma, and I don't really care about the increase in this kind of regularity exponent. So I can just truncate my expansion up to level gamma, and I am again in d gamma. So this is a small exercise if you want, that if you truncate an expansion in d gamma plus 2 to level gamma, then you are in d gamma. Okay, it's very so it's true in the classical setting. It's true also in this setting. Now, in fact, what do you do? So you apply I to u of x. So all symbols you see, you apply an integration symbol. And then you add a function at level 0 and 3 functions if you want at level x1, x2, x3, the classical monomials. F and gradient of f are explicit, and so they are contained in what Felix explained, but okay, it's not really important for us what they are explicitly. They exist, they are explicit. So there is just one additional convention. In U, you already have 1 and xi. Every time you encounter the symbols I of 1 or I of xi, you put this to 0. And this explains why you wanted k to integrate to 0 the functions y and okay. So these are maybe small technical details, but you will see later where we apply this. And pi less than gamma is a projection. Okay, you project everything, because here you increase by 2, so you will go beyond the gamma, and then you throw away everything which is beyond gamma. Okay, we will do the precise computations for phi for 3. You will see how this works. Okay, okay. Maybe I'll come back to the statement when it is useful. Okay, so this is one operation you can do on model distributions. Integration. So we need another operation, because in the phi for 3 we have a u cube, so we need to multiply model distributions. Okay. Okay. First a question. So you have 2 functions, f1 and f2, which are c gamma 1 and c gamma 2 respectively. These are classical order spaces with positive exponents. So a question for you: what is gamma such that the product is in c gamma? You can choose among these. Yeah, whatever. I can add the sinus hyperbolic if you want. Okay, since yes.
Is this minimum or maximum?
Minimum.
Third, I would say.
Okay, very good. This is a physicist's intuition. That's the right answer. Yes, of course. So. There is no reason to improve the regularity by the product, so it is the worst between the two of them. Okay, so this is the classical principle. So is this going to be still the case? Okay, the situation is a bit more complicated. So what have I? Yes, okay. So in fact, you need another small notion. So you will say that f, so a model distribution is in d gamma alpha. Okay, if f is in d gamma, and in its expansion, you only have trees which homogeneity, whose homogeneity is bounded below by alpha, where alpha is okay, it may be 0, but it may be strictly negative. So, okay, again, I will show you very concrete examples. So now you have 2 model distributions in d gamma I alpha I, and then in fact, so you define gamma as follows. So it's gamma 1 plus alpha 2 inf gamma 2 plus alpha 1. So notice that alpha 1 and alpha 2 may be strictly negative, so they are less or equal to 0. So in principle, this is less than gamma 1 inf gamma 2. Okay, then you define f1, f2 of x as the pointwise multiplications of the two objects, but you truncate at level gamma, so you throw away anything which would be of homogeneity greater than gamma. And then, so there is a small theorem that says that f1, f2 belongs to d gamma alpha 1 plus alpha 2. Okay, so which means that in the good cases, which means when the pi are continuous, but not necessarily in the canonical setting, so you can define, you have a notion of product, which is this one, so f1 times f2 will be the reconstruction of this capital F1, capital F2, which will be, okay, this expression. Okay. So again, it seems that we are kind of cheating because this looks completely formal, but the point is that you have the reconstruction theorem, which gives you back a concrete object. Okay. So this is really a good notion of product of model distributions, which works if you have sufficiently good coefficients. So in particular, notice that if you want to apply the reconstruction theorem, the best case is when gamma is positive. So this is anyway putting some constraints. You need gamma 1 plus alpha 2 or gamma 2 plus alpha 1 to be positive. Okay. Again, so this will be more clear when we do the computations on 543. Okay, we'll come back to this. The message to understand now at least is that there are theorems which allow you to operate on these model distributions by multiplication and by integration. Okay, so how do you want to use this? I remind you, we are in this setting. There is some PDE, which is this one in particular. And then we want to find a model distribution, which is modeled by the canonical model. So I remind you again that this space depends on the model you have fixed, such that when you reconstruct capital U, you get U epsilon, which means that capital U is a Taylor expansion of U epsilon. So we'll see now that such capital U must take this form. Okay, so, and this is again the tree which was missing from the list, where you have some phi here and some say gradient phi. By the way, this does not mean that phi is differentiable. Okay, it's just with analogy, in analogy with the classical Taylor expansion. So these are two objects which are not necessarily one the gradient of the other. But so this is what multiply x, and this is what multiply my 1. Okay, okay. Let's see. So again, gamma is 1 plus 3 kappa. The aim is to write U as the fixed point to a lift of the PDE. Now the lift is this. So okay, sorry, I did not write this in the mild formulation. You can write this as U epsilon. Maybe I do that. I should have done so. So U epsilon is, okay, G convolution psi epsilon minus U epsilon cube. There is the initial condition, so I forget about that. Okay, so you see, this is the lift of this PDE to the my space D1 plus 3 kappa. Okay, I have defined the integration and multiplication in order to make sense of this. Now let's see. you will see this is going to be completely symbolic calculus, okay? But I can do this. I mean, this will have some significant impact as soon as I apply the reconstruction theorem. But at the moment, I am just at the level of symbols. So this is a finite family. Okay, U has to be just a sum of coefficients times symbols. Then I plug this in. So this must be equal to, now k of psi is just this. It's I of psi minus I have sorry, here I am applying the what is it, this theorem, the integration theorem. I am using this expression, so I am applying I okay, I am taking the cube, so I have tau 1, tau 2, tau 3. I apply I project, I have a minus, okay, plus two functions as in the theorem, okay. Now before going into more precise computation, so we notice that on the right, okay, so I have this which is here, I have this which is here, but this is I of something, and this is also I of something, which means that on the left all coefficients are 0 unless tau is I of something. Okay, so if you check the list, there are only 3 such trees. So I can go back to the list. Not very efficient, but yeah, you see. So this is not I of something. This is not. This is not. This is. This is not. So because there are products, you see, there is a branching point at the origin, the root. Not. Yes. Not. Yes. Okay. So that's very, very simple. So I have already simplified a lot my list, okay, of coefficients. Okay, now I have to find A1 and A2. Okay, recall that it's like this. We have to compute psi minus U cube. Now I apply multiplication, so the theorem. So note that U is in 1 plus 3 kappa, so D1 plus 3 kappa, this is gamma, and alpha is, so this is the element with lowest homogeneity. And the homogeneity was minus 1/2 minus kappa. Okay, so I start from U times U, so I have to compute, okay, I go back here, yes, here. Gamma 1 is equal to gamma 2, alpha 1 is equal to alpha 2, so the inf is the same. So I have just to take the sum. The sum is 1/2 plus 2 kappa. Good, so U square is here, and alpha 1 plus alpha 2 is twice this, so minus 1 minus 2 kappa. Okay, I don't make the formal computation for the moment, so I go on. I know that U square exists by the theorem. Now I have to multiply it by U. So now I have to consider this plus this, which is kappa, and this plus this, which is kappa again. So the inf is kappa, which is positive. Great. So U cube is in D kappa. Okay, if you want, now I don't really need anymore the lower exponent. And then I can just, again, a bit formally take the cube of this expression with a minus. I get a number of elements. So these are all of, if you check the homogeneity, so this is minus 5 over 2 minus kappa. This is, so anyway, all these, wait a second, no, this should not be there. Why is this there? I should be stopping at kappa, so this should not be there. So this can be there. This I don't remember how much. So this is yeah, this is still negative. This is the same. It's still negative. So okay, the only one which I should have thrown away is this. But again, I think this is a mistake in Martin's paper. Okay, I will check this. So the idea, in fact, it doesn't really disturb you if it's there, but you don't need it. It's like an error of a larger order. Okay, and now the point is that you are in d kappa with kappa which is positive. Good. So now you can apply the integration operator to it, which is what I'm going to do in the next slide. But now you see why I chose gamma equal to 1 plus 3 kappa, because if you choose for instance 1 plus 2 kappa, then at some point you lose, and here you are in d0, which is not good for the integration operator or for the reconstruction theorem, for instance. So you choose this exponent in order for this operation to give in the end an object in a positive regularity space. Okay, because what you have below here you cannot choose. The alpha I are given, while the gamma are, so you have some freedom on that. And also, why did you choose in the first place this list of symbols? Well, because you see you start from xi, which has to be there. So you know that three elements will be there. It is xi, they are xi, 1, and x. Okay, you have the noise, and you have classical monomials. If you want also x square, x cube, etc. Then you start applying formally, if you want, this operation, which is it's the PD. Okay, it's the right hand side of your PD, and it's your nonlinearity at least. And you generate all these elements. Okay, actually, sorry. What you apply is also the integration. I'm sorry. So what you apply is not just this, but it's k of xi minus u cube iteratively, and you see all these elements, symbols which appear, and then once you have decided what the level of truncation is, you stop. Okay, so again, it's formal. It looks completely formal, but the reconstruction theorem is what is behind to make all this meaningful. Okay. If there is no question, then I've lost you. Yes.
Aren't you missing the term where with the tree with two noises and that are multiplied, and the
two noises?
Well, with the
I think the x term with the grad phi should have the cherry in it.
yeah, that's it. What I'm trying to say.
What you mean? There is a xi there? Maybe. But again, I copied this from Martin's paper. Then I checked up to a point, and okay, it's good. So you say here there should be maybe xi or
Cherry.
what is a cherry? Okay, the cherry. Okay, I see. Yes, which indeed appears this. Okay, then it's negative. Okay, good. That's why it's there. Okay. Yeah. Okay, good. Or maybe I did a bad LaTeX manipulation. Okay, good. So indeed there is another. Yes.
So you put in the U, no, in the you put phi and grad phi.
Yes.
Can you repeat maybe?
Yes,
why?
because U is in D1 plus 3 kappa, Okay, and so you also have a
Yeah, but why the coefficient is grad phi?
no. Okay, I said this. It's just a notation. It does not mean that it is the gradient of phi.
Okay.
Phi is not differentiable.
Yeah, sorry.
Yeah. Okay. Okay. Now again, I have this. Now you apply the integration as here, and what do you get? So you apply I to everything, but you stop at level 1 plus 3 kappa, and in fact only 3 trees remain. All the rest is thrown away, and plus you have some function psi multiplying 1 plus some function gradient of psi multiplying x, and so now you have to compare this with your expression for u. So you still hope that u is a fixed point of this map, and so you compare these two quantities, and you realize that a1 must be equal to -1, a2 must be equal to -3 phi, psi must be equal to phi, and grad psi must be equal to grad phi. So, and then you have shown that this is the necessary expression for your putative fixed point of such an expression. So this was really completely formal computation. Okay, other questions? Now, the solution map. So we note that, in fact, until here, these computations hold for any model, pi and gamma. Okay? So for any such model, we construct the associated d gamma space, and then we set the fixed point problem u equal to k psi minus u cube. So yeah, so okay, let me finish and then we can comment. So we define a map on d gamma which will be a contraction on a small time interval. So okay, unfortunately, in order to make this a contraction, you need something which is less than 1, okay? And this is not the case in general unless you consider a small time interval. So this is where you have this restriction, which seems to annoy, okay, it's legitimate, so several people. And then it means that you have to work on ad hoc arguments in order to extend the solution, if it is possible. And then you define u as the reconstruction of this fixed point solution. Okay. So in my original picture, so this is the way you construct this map, this arrow, lambda. Okay. So you have any model, you construct the associated d gamma space, you set a fixed point problem, you solve it, and then you reconstruct. So and you're done here. Okay, then you should prove that this map is continuous. Okay, this is this takes some time, but it is because all these operations that I have defined come with good control of the norm in terms of how the model moves. So by the way, we have not even defined the topology models, but okay.
So,
Yes.
if I just iterate that equation, I'll generate an infinite series of trees, right?
Yeah.
Which are all formal symbols at the moment.
Yes.
Right. Now, well, how do I know whether this series is convergent? I mean, you need short, as you
Yeah.
say, you need time short.
No, okay, yes. But in fact, you truncate. So at every, all series are summed here. Okay?
You're going to truncate the series.
No, okay. No.
Then there's no need.
You start, what is it? With a fixed values gamma equal to 1 plus 3 kappa, which determines, together with the nonlinearity, so how many trees you have in your business. Okay, these are all the trees you're going to see. If you generate more, you throw them away.
So actually, then it's just it's the coefficients of, in front of
Yeah, exactly.
symbols which
Yes.
are being determined.
Which contain some information. Yes.
Those are infinite series.
They are functions. They are rather integrals. So, okay, let's see. Good. So, it's a very good question. Also because, so this is the last slide I have prepared. So it's good that you have questions. So, okay, let me write this on the blackboard. So you start from D. So not U. U will be the fixed point. You start from V. So what is your map? What is a free letter still? I don't know. Z. Okay, from D gamma to D gamma. So Z of V. So will be this K psi minus V cubed. Okay, so these are the computations that I started with U. Okay, in a sense, this is what you get at each. Okay, so suppose that V has coefficients. So V of X is a sum, or tau is in T, but this is this finite list. Okay, there are like I don't know, 12, 15 terms. That's it. Of some coefficients, b tau of X times tau. Okay, of course, all the information is here, where inside these functions. Now you apply once your map. Now the non-trivial operation is here and here, exactly what I have not written. Okay, so but let's see. This should be easy to describe. At least what is phi, for instance. As long as the model is smooth, we can compute everything. Yeah, so Z, let's say again, so Z of V will be necessarily, so there is K of psi, which is this tree. Okay, minus, there is this projection of all this sum B tau 1, B tau 2, B tau 3, I of tau 1, tau 2, tau 3. Okay, plus you have this, let me call it phi 1 plus grad phi X. Okay, yes, you agree? So now again, this comes from V, so nothing very deep actually happens here. Okay, phi is, this is the more precise content maybe of the integration theorem, yeah. So phi is given as a convolution between this and R of V of X. So okay, gradient phi is something like this as well. Yeah, and then you will go on. So in fact, I mean, the principle of a contraction is that you iterate it, right? So you start from anything, so the zero function, and when n goes to infinity, this should converge to the fixed point u. Okay. So I've never done myself this computation, but
So I see then that, I mean, it's really phi will get more, will become a series when you do this.
okay, at least no. Phi anyway changes at each stage. It's not the same phi.
It
Okay.
becomes a very nonlinear function of v.
Yeah, of course this is nonlinear because you have this part which is nonlinear.
And it looks so. It looks to me like it's a power series in the.
Oh no! By the way, this is not. No, sorry. No, this is wrong because sorry. No, this is wrong because you are integrating. You're not integrating v. You are integrating psi minus v cube. Okay. No, sorry. So this is already at this level. This is nonlinear. Okay, sorry. That was wrong. So this is more correct. Okay. So this is the. Okay, maybe we should. Yeah.
Is the lifetime deterministic in the end, or is it random?
No, it's random.
But so you solve it in this abstract space.
Yes.
Here there's a deterministic.
Yes. At this level, everything is deterministic once the model is fixed.
So
The randomness is in the model.
So once you project it onto the whatever it's called, the real equation,
Yes.
The lifetime becomes random. So here it's somehow there's no randomness, right?
Okay, good. So
Well,
again,
at the level where you solve the equation here,
yes.
there's
So
no
the randomness is inside the model. Okay. So today there is nothing random. Everything is deterministic. This is PD. Kind of weird, but it's PD theory. Okay. And so the answer is the lifetime of the solution depends on the model. So if the model is random, then okay. But here everything is deterministic. There was no.
What?
Yes.
Can I
Please.
comment on this? So
Yes.
So the I mean, so as Lorenzo said, you're setting up in a nonlinear PD type. You're setting up a fixed point argument. You never write actually down a power series or an iteration. You just use Banach fixed point theorem, which don't worry how it gets. It gives you a fixed point. But then I mean, you need the contraction. So you need to go kind of to a small space in your function space, and how small this ball has to be in function space depends on the constants which appear in the continuity property of the model, right? I mean, there was this, what I call constant C, and that in general is a random constant, right? I mean, if you're at some bad point in space, that might be unluckily large, and that then will force you to have a small existence time. So the randomness sits in these constants that describe the model, I would say.
Yes. Thank you. Okay, and this is very important that all this. Okay. Let me go now. Yeah, I repeat it. So all these computations hold for any model. So again, you have seen only one model until now. Okay, but it is very important to know that for any model you can do the same computations. In particular, the form of this PDE does not change. okay, of the lifted PD. Now, let us go back here, let us reconstruct, and we obtain now U epsilon. So now we are in the canonical model. So U epsilon is defined as R epsilon U, which is this. Now we apply the commutation. So this is the convolution between K and R epsilon psi minus R epsilon U cube. And this is K convolution psi epsilon minus U epsilon cube. So this is the regularized PD. Apart from the fact that K replaces G, but we neglect this, and so therefore this is the regularized PD. Okay, but here, which is equivalent to that. But here you have used the property of the canonical model of being multiplicative. So otherwise, this is not true in general. It is not true in general that the reconstruction of the product is the product of the reconstruction. I've never stated this. It's not at all in the reconstruction theorem. Okay. So here I am using a property of the canonical model. So that's why when tomorrow we renormalize the canonical model, so this, I mean, until here everything will work the same way, but the final identity may be different. I may find a different expression for this for the reconstruction of the cube. For instance, I may find the C epsilon U epsilon minus U epsilon cubes. You see? Someone was asking me, what about here? What about U hat? So what PDE does U hat solve? So U hat is the limit of the renormalized, regularized solutions. Okay. Okay. Small U hat may not satisfy directly a PDE. Okay. But the capital U hat will satisfy this with respect to this model. Okay, so maybe we see this tomorrow better. But so it means that once, okay, yeah, once you have fixed all these, sorry, I have to go back to the pi's. Yes, all these pi's, okay, will be somewhat changed. In particular, this will be changed, this will be changed a little bit, okay. Once you have described these quantities, okay, then you can interpret your PDE at the level of the model distribution. But this will be your new concept of product, okay. So at this level, you will have this minus an infinite constant, okay, but which means that you are actually centering the random variable. You see, so once again, so once you have correctly defined a finite number of explicit products, then you can set up all this machine of formal, so symbolic calculus. In particular, this makes sense. So this makes sense, and by reconstruction, you get some concrete distribution. So the concrete distribution itself maybe does not satisfy a PD anymore, in the sense that yeah. But it comes from an object which satisfies a PD. Okay, so tomorrow, finally, we're going to see the infinite constants and this procedure which goes from x epsilon to x epsilon hat, which is the algebraic operation. And then, okay, the convergence of x epsilon hat to x hat is another very, okay, big result, and I can maybe say a few words, not more. Okay, thank you very much.
Do we have any questions besides the ones that have already been asked? Yes.
So you're neglecting the difference between K and J. Is that complicated at the end, or?
I am also neglecting the initial condition, and in fact it's the same, so you have to add here a kind of smooth term, but which is easy in comparison with the rest.
Okay.
Okay. No, there are other problems, but this is the main skeleton of.
So does the initial condition have to be smooth, or can you?
No. Okay, this also depends a bit of the equation, but here you can like have C minus 1/2 minus something, and it operates on.
Okay then. Well.